In the last video for Chapter 2, we're going to be looking at two variable inequalities. So just to recap from Algebra 1, how you would shade for an inequality. If I had y is greater than x, that's when you have that dashed line, and shading above would look something like that. Y is less than x, same deal, you have a dashed line, but here's what it would look like if I was shading under that line. Greater than or equal to, I have a solid line shaded above. Less than or equal to, I have a solid line shaded below. So if I want to graph a simple linear inequality, it's the same thing as graphing a regular line. I just need to kind of add two steps in the end. I need to ask myself, do I have a dashed or solid line? Basically meaning, do I include that line in my solution? And do I shade above or below? So for y is greater than 3x minus 1, this is easy in the sense that this is already in slope-intercept form, so I could just go ahead and graph from here. My y-intercept is -1, so I'm going to plot my first point there. And my slope is 3, so I count up 3 over 1. So I'm going to keep doing that for the rest of my graph. So then, in the end here, I'm going to look at that inequality and answer some questions from here. I have y is greater than 3x minus 1. So since it's greater than, I don't see that line below it. That means I want to shade everything above that line, but I don't want to include it. And how I represent that is by a dashed line. Finally, if I want to be shading above it, kind of a weird trick that I always used, my 6th grade math teacher taught me this a while ago and it always stuck with me. If you're ever unsure about what above or below would look like, I treat this line as if it's a roller coaster track. And I draw a person on a roller coaster with it. If I want to shade above, I would want to shade above the person kind of towards the sky. So here. So if I want to shade above this line, I shade in like so, and that's my answer. The last thing that you could do other than the roller coaster theory is a little more proper to use a test point. So a test point is another way to double check your shading to see that you're shading in the correct area. Something to keep in mind is that this shading indicates that any coordinate in that orange shaded region would be a solution that would make that inequality true. So what I'm going to do here is I'm going to pick a coordinate in what I just shaded in orange, and I'm going to see if that holds up in my inequality. So here, let's pick -3, 0. Again, I could literally pick any coordinate in this shaded region. If it's the correct area, any of them should work. If I'm testing -3, 0, I'm going to plug in -3 for x, 0 for y, and see if this inequality holds up. So now I have 0 is greater than 3 times -3 minus 1, which simplifies to -9 minus 1. And I'm left with the inequality that states 0 is greater than -10, which is in fact true. So now I know 100% for sure I shaded in the right region, and I'm good to go. That's my answer. Let's look at one more example. Here I have -2y is greater than or equal to 4x minus 6. So right out the gate here, this is a little bit more complicated in the sense that we are not in slope-intercept form yet. Slope-intercept form, again, basically just means I get that y isolated or by itself. So in this problem, all I'm going to need to do is divide everything by -2. I wanted to go over this example just as a reminder that when you're working with inequalities, remember here, since I'm dividing by a negative number, that's going to flip this inequality. So when I do this, now my inequality is going to say y is less than or equal to -2x plus 3. Now I'm in slope-intercept form. I can graph just like I did in the last problem. Here my y-intercept is +3, and my slope is -2 or down 2 over 1. From here, I'm going to look and I see that since it says less than or equal to, that means that I want to include that line in my solution, or in other words, I'm going to be making a solid line here. Finally, again, if you want to use the roller coaster theory, if I draw a roller coaster, if I want to shade less than, think about shading the tracks, or I want to go below the person. So I'm going to be shading in this region and go from here. Finally, the most proper way to test this, again, is to use a test point. For this, let's use the test point 0, 0. I'm going to use my slope-intercept form of the equation. You could use the original one if you want to as well. 0 is less than or equal to negative 2 times 0 plus 3. That simplifies down to 0 is less than or equal to 3, which is in fact true. And then finally, just to show you an example of where this wouldn't work out, let's pick a point outside the region to see that this wouldn't hold up. So let's do the point 2, 3. That's clearly outside on the other half plane of this graph. So now I'm going to have 3 is less than or equal to negative 2 times 2 plus 3, which simplifies to 3 is less than or equal to negative 1. 3 is not less than or equal to negative 1, so that would not work. That's an example of if you pick a test point, it doesn't work out. That means that should not be the region that's shaded. Finally, let's end the day by incorporating absolute values in here. So here I have the equation y is greater than or equal to 2 times the absolute value of x minus 1 plus 2. So in these equations, I'm going to use what I know about the general form of the equation. I'm going to graph. Sometimes with absolute values, it's a little bit easier to shade above or below because you're going to look at your vertex and either shade above that or below it. So here, looking at my graph, my vertex is 1, 2, and my a value or my slope is going to be positive 2. So from that vertex on either side, I'm going to count up 2 over 1 to make my V shape. Next, I'm going to look at my inequality symbol. I see I have greater than or equal to, so I want to include that line, so it's going to be a solid V. From there, I want to shade above it, so I'm going to look at my vertex, look above it, and shade in there. Finally, let's end the day doing one more example problem. Here I have 3y is greater than negative absolute value of x plus 2 plus 6. So here I'm technically not in general form yet because that y is not isolated. Similar to that other example problem that we did, the only thing that I need to do to get y by itself is to divide everything by 3. Also notice I'm dividing by a positive number, so I don't need to worry about flipping that inequality. When I do this, I get y is greater than negative 1/3 times the absolute value of x plus 2 plus 2. Also, just keep in mind and notice that when I divide that absolute value, I'm not going to work with that 2 inside of it. Think it's like trapped in there. I'm going to be dealing with the coefficient outside of it, so that's why it looks the way that it does. Now I'm in general form, so I can do the vertex, the a value, and go from there. My vertex is negative 2, 2, and my a value is negative 1 over 3. So I'm going to plot my vertex. My a value is negative 1/3, so I'm going to count down 1 over 3 on both sides. Finally, looking at my inequality symbol, it's greater than. I don't want to include that line, so I'm going to make it dashed. And finally, again, I'm shading above, so I look at that vertex, I go above it, and I shade like so. Finally, just as a good measure, since it doesn't take that much time, I would highly recommend always doing a test point, especially in something like a test or quiz. For a test point, let's check negative 2, 4. I plug that in. I have 4 is greater than negative 1/3 times the absolute value of negative 2 plus 2 plus 2. Simplifies down like this. Negative 1/3 times the absolute value of 0 is 0. And I'm left with the inequality 4 is greater than 2, which is in fact true, so I know for sure that I shaded in the correct region.